copy, so it has to be my office. I have to be able to get it to my office. Emails typing to the environment, I will answer them quickly as possible. So this chapter 4, which I left off the exam, is on cycloalkane. It's talking about cyclic alkane. Now, still alkanes. These are the simplest organic compounds. So we're looking at them to keep things as simple as possible in the beginning. This is where you need to use line drawings. If you haven't been working with them, you need to step up to the line drawing mode to deal quickly with cyclic compounds. The cycloalkanes have all carbons in the ring. That's not necessary. You can have other atoms in the ring, like oxygen or nitrogen or sulfur in particular, but then it wouldn't be a cycloalkane. There's a whole ton of cyclic compounds that contain what we call heteroatoms, atoms other than carbon, like a nitrogen, for instance, is very, very common. And that's what we call a heterocyclic compound. Now, it can be oxygen, can be sulfur. Besides carbon, nitrogen, oxygen, and sulfur are the three bridging atoms that you typically find in rings, particularly in natural products. If you take, say, 1,000 products from natural sources, about 80% of them will be heterocyclic compounds with nitrogen, oxygen, sulfur in the ring, etc. We definitely don't want to deal with that right now because it seriously complicates things. Heterocyclic chemistry is one of the last things that you study in organic chemistry. We're just going to talk about what we call carbocyclic rings, where it's all carbon. And that makes it relatively simple. Now I'm using Tenside up here rather than models because it's easier. But for an open chain compound, let's take 3 carbons. So I'm just going to draw a string of 3 carbons. That, of course, will be propane. And add hydrogens to it. And optimize the structure. And you're all familiar with this. Every carbon here is tetrahedral. All the bond lengths are sort of default. The ideal carbon-carbon single bond length, sp3 is about 1.5 angstroms. A double bond length is shorter, and a triple bond length is shorter. You can easily remember it as 1.5, 1.4, or 1.3. It's really the sigma bond that determines the distance between the carbons. High bonds are kind of floppy and don't really affect that all that much. So an sp3 sigma bond is the longest because it has the most p character, 75% p, 25% s. S orbitals shorten the bond, p orbitals lengthen the bond. sp3 is longer than sp2, which is 1/3 s and 2/3 p, and sp is the shortest. The sp sigma bond is 50% s, 50% p. But with those carbon-carbon bond lengths and typical carbon-hydrogen bond lengths, which is almost always about 1 angstrom, that virtually never varies, maybe 1/10 of an angstrom, like 1.1, that's about it. So with 109.5 degree bond angles and appropriate bond lengths and an optimized structure, where if you look down any of the carbon-carbon bonds, you see everything is staggered. Let's look at this in the ball and stick mode. It's easier to see. You can see if you look down this carbon-carbon bond, that everything is staggered. And that would be true down the other carbon-carbon bond also. So the program has produced what is the best structure it can be given the molecule. Remember, the whole idea is to get all of the electrons close enough to bond the atoms together in the stablest way possible, but also to keep them as far away from each other as possible by rotations around the bonds. That's the ideal. And we can calculate the energy for this. Let's do that. Okay, so there's the energy. See, the total energy is 1.5 kilocalories per mole. That's essentially zero. What this program does, and actually even the more sophisticated programs that deal with things like proteins and nucleic acids, is it assigns not energy values, but actually energy penalties or defects from the ideal molecular structure. Propane is essentially ideal. So 1.5 in computational chemistry is considered zero. That's a trivial amount of energy. Now it is distributed through a bond angle energy. That's how close the bonds are to the ideal, 109.5, and you can see that's essentially zero. The bond stretch energy is the bond length. How close is the actual bond length to the ideal? 1.54 angstroms for the carbon-carbon bond, 1 angstrom for the carbon-hydrogen. And the bond torsion energy, that has to do with staggered and eclipsed, the rotamers. And since it's staggered, that's essentially zero. Now there's some other terms here that you don't need to worry about. But the main thing is bond angle, bond length, and torsion, which has to do with the staggered and eclipsed conformations. Now let's put this into a ring and see what happens. So instead of the open chain propane, let me just close this. Let's build a 3-membered ring, which would be the smallest carbocyclic compound you could have. 3 carbons. We'll add hydrogens to it and optimize the structure. You can see that the 3-membered ring is flat. The bond angles, though, are squished. Instead of being 109.5, that's a perfect isosceles triangle. They're 60 degrees. So 60 instead of 109.5 causes electrons to be too close to one another. Let me see here. So this is an orbital view. You can see in the center of the ring how the yellow shading, those are the carbon-carbon bond orbitals, and you can see how crunched together they are. That's going to cause electron-electron repulsion, which would register as angle strain, because it's really the compressed bond angle that's causing this to occur. Now, there's another problem here, and that is if you look down any of the carbon-carbon bonds, you can see everything is eclipsed. If you have a flat ring, any substituents that come off the atoms in the ring are lined up like bowling pins or a picket fence. They have to be staggered. You can't rotate around the carbons in this ring. That's an important consideration. That ring is locked in place. When you take the open chain and close it, that prevents rotation to any any significant extent around the carbons. And if you make a plastic model, you'd see that the price that you pay for twisting is that you make the bond orbitals even closer together than they already are. So it's not allowed. You can't rotate completely, at least, around the bonds. So if we calculate that energy again, it should be higher. Okay, and it's significantly higher, essentially 107 instead of 1.5 kilocalories per mole. So it's going up over 100 kilocalories per mole. If you look at the bond angle energy, that's 99. Almost the entire problem is the bond angle compression, which is pushing the electrons too close together. The bond stretch energy, which is the length, is still almost zero. The bonds in cyclopropane are perfectly normal in terms of their length, but there's electron repulsion in the angle strain. And notice the bond torsion energy, that's the staggered eclipse thing. Instead of being zero, it's now close to 6 kilocalories per mole. Less of a problem, but clearly higher than the staggered form that you could get in the open chain. This can't get staggered, it's permanently eclipsed. So cyclopropane is less stable than propane. And when you mean cyclopropane, you should say cyclopropane, or write cyclopropane. For an organic chemist, cyclopropane and propane are as different as a bus and a car. They're two totally different compounds, so don't confuse the two. And they're not even isomers because the formula is different. This is C3H6. Open chain propane is C3H8. Remember, the ring is 1 degree of unsaturation. Now, what does this mean in reality? Well, not a super amount, because cyclopropane is still a relatively stable organic compound, stable enough to exist at room temperature indefinitely. Propane is more stable, but cyclopropane is not an impossible structure. It's actually just a little less stable than propane. Okay, so what happens as we go up? Well, let's go to 4 carbons. So here's a 4-membered ring. It's going to have 8 hydrogens on it. We optimize it. You can see it's just bigger than cyclopropane. A little more breathing room. The bond angle is 90 degrees instead of 60 degrees. So if we do that calculation, the total energy is 34, and the bond angle energy is 21. In cyclopropane, it was 99. So it's gone from 99 to 21 because the ring now is bigger, and that moves the electrons out a bit. It's 90 degree internal, not 60. Now that's not as good as 109.5, but it's getting better. Notice it's still planar, and everything is still eclipsed. So the torsion energy is 10.17. That's higher than it was for cyclopropane, but it's cheating to compare them because cyclobutane has more atoms. This is a total eclipsing strain around the ring. So it's got 1 more CH2 than propane. Per CH2, it's about the same. Then when we go to 5, you see very much the same thing with a little twist to it. So let's see, 1, 2, 3, 4, you can use up in the computer lab across from the organic lab, by the way, anytime you want. Okay, so you have a 5-membered ring now. Let me put it into what's called a tube setting here. This is a 5-membered ring. You might notice that it's not exactly flat. One of the carbons is slightly twisted out of plane. That's an important thing to notice because, and it should make some sense, as the ring gets bigger from 3 to 4 to 5, it gets a little more breathing room in terms of ability to twist around the carbon-carbon bonds. It can't twist very much, but it can twist a little bit. And the advantage of that, let me optimize this again. The advantage of that twisting is that it gets, if you look down, this carbon-carbon bond right here, you notice it's sort of staggered. The other bonds are still pretty much eclipsed, like this one right here, but it's trading a little more angle strain for a little less torsional strain. So it's sort of like what you would do if you put on, say, a shirt or a sweater that's too tight. You kind of start wiggling, trying to get yourself as much room as possible to be comfortable. The molecules do that. It can't twist too much, or the angle strain will zoom way up. But it can twist a little bit in exchange for lowering a little more of the energy in terms of the torsional strain. But it's still basically flat. It's called the envelope shape because I've exaggerated it there, but 4 of the 5 carbons are in the same plane, and 1 carbon is a little bit out of the plane. So it looks like an envelope sitting on a table with a flap sticking up, called the envelope shape. And because of collisions, at any moment in time, only 1 carbon is out of the plane, but it can be any of the carbons. So if you imagine this dynamically, it would sort of be like a ripple or a flutter around the ring. So it's almost like a flopping bird. It's wiggling like that. And each carbon takes a turn at moving out of the plane. But you should still think of it as basically locked in a flat position. So 3, 4, and 5, think of them as flat. Now we can calculate the energy here. And you see the total energy, 10.7. It continues to go down because the bond angle is actually pretty good. You see right here, it's only 2.2 kilocals per mole. In a 5-membered ring, the geometric internal angle is 110 degrees. That's pretty close to 109.5. So the bond angle isn't a problem with cyclopentane. It's all pretty much in the eclipsing, in the torsional strain. So the bond lengths are fine, the bond angle is pretty good, but the bond torsion still adds up. And you have 5 carbons and 10 hydrogens, so it accumulates. Still, this is a very stable structure.
What did you say the bond angle was for this?
110. Okay. Now, what happens if we go to 6 carbons? Then it gets much more complicated.
Oh.
Not working. Okay, so let's draw a 6-membered ring. And I'm kind of being sloppy about it, doesn't matter. 1, 2, 3, 4, 5. 1, 2, 3. This needs to come here. Oops. Okay, so there's 6 carbons, 12 hydrogens. We'll optimize it. Do I have 7? No, that's 6. Okay, if you look at it, it's kind of a strange shape right here. Oh, wait, 1, 2, 3. Okay, it's sitting now in one of its favorite shapes.